All right, so welcome back to fourth day of CosmoLattice School. Second activity of today is our 8th lecture, where we're gonna learn from Ken how we can do nice plots with CosmoLattice, or at least using the output from CosmoLattice. Ken, the stage is yours. Please go ahead.
Yeah, thank you very much. So hi everybody. Thank you for attending. This will be a bit more of a light lecture today, and we won't fill the whole hour. So I might take like 40 minutes, and then we have a longer lunch break. So today I'm going to talk about plotting 3D data with CosmoLattice. So this is more of a light lecture, and the goal of this lecture is does the slideshow change? Oh, okay. So the goal of the lecture, some of my cursor is not working, but okay. And the goal of this lecture is in principle that you can output your lattice, your 3D lattice snapshots and print them and make beautiful pictures as you see here on the right. So as a short motivation, why we might want to sometimes output such data, for that purpose, we look once more at this potential you've seen before here. So we have just this tangent hyperbolicus potential with a squared term here now. And now, yesterday already a question appeared for this capital M, where we use now very small values here. So what we effectively have, we have here this inflection point, phi I, which is marked here by the dashed line. And the infraton rolls up here downstairs, right? So it starts in this tachyonic region and then enters here this minimum. Now, this tachyonic region leads to also some resonance effect, which is called tachyonic resonance. And you can see that here we have this we have the different energy components, the kinetic and potential energy in the beginning, where the system is mostly dominated by the homogeneous mode, and then you see how the gradient energy indicated here by the light blue one grows very quickly when the infraton enters the tachyonic region. Then this so-called back reaction happens, and then somehow the system gets into a stationary regime, right? And this part looks fairly boring, one could say, and you might assume by studying this average quantities that not much is happening here, right? But effectively, what you can see, and which you only see if you look carefully on your snapshots, is that in this part here, there are some oscillons forming, right? These are like metastable configurations which are very long-lived and oscillate very longly and eventually decay, right? And these configurations you would never see by just studying, or maybe if you have a good intuition, but it's not that easy to see from a spectrum or any other average quantity, right? So sometimes it's useful to study to output your snapshots or your lattice and study your box and see what phenomena happen. So what you see here are the over energy densities and different contours of it. We come back to that later. Once again. Okay, now these snapshots are taken in CosmoLattice by the energy snapshot measurer. You can find it here in the measurements, down here in the measurements folder. And it outputs your snapshots in so-called HDF5 files. So CosmoLattice uses the HDF5 library, which is a library which is able to store big amounts of data very efficiently and structure them also fairly well. So in science, it's fairly commonly used. And you can imagine that every time you output a lattice, your whole lattice, you don't need compared to the, I don't know, mean field, just one entry, you need n-cubed numbers, right? So that can become fairly big amount of data. So this HDF5 file, if if you open them in a text editor, so you just get weird stuff here, right? So you need to have a program which interprets these files properly. So you can do that with Mathematica, MATLAB, Python, Gnuplot, etc. But you can't open it just like the other average energy density files within a text editor and quickly look into it, right? You need an appropriate program for it. Now, the HDF5 files in CosmoLattice are saved as follows. So it outputs you these types of files which have this structure, where in the first part you have the type of your energy, which are in case of the scalars, your kinetic and gradient energy, and for the gauge field are called electric and magnetic. So these are put here as type, and in the back part you have the field type written like scalars. You can output scalars, complex scalars, SU2 doublet, and in case of the gauge field, U1 and SU2 doublet. So these short notations are written in here, and kinetic and gradient and so on are written here. And then you have at last the potential energy, which is outputted with the following notation. Okay. These HDF5 files are structured as follows. So this is in general, they're all structured in groups and data sets. And if we, for example, take now the kinetic energy of a scalar field in CosmoLattice for two scalar fields, you have the following structure graph of your HDF5 files. So you have in blue your groups and in orange your data sets. So you have here two groups. One's the kinetic energy of the first order field, since we have two order fields, the first order field, and here of the second order field, of the second, sorry, not order fields, of the first scalar field and of the second scalar field. And then you have your data sets as subgroups of it, right? And they're always indicated by the different timestamp. So here, for example, we have just an example where we have taken 0, 10, 15, 20, and 5, and they're really structured in this way, right? So they appear first appears the 0, then the 10s, 15s, 20s, and then 5th. So it's always ordered after the first number. So you have to be careful to if you want to plot a series of snapshots, that you sort them correctly, and not this. That not the 5th appears at some point, you get confused or so. Okay. For this information, for example, in Mathematica, you can just get information by importing your kinetic energy snapshot and then put summary and structure graph. We will see that later. I will show you later more about that. Okay. Then the groups you've seen before, you've seen in blue, are shorthanded as follows. So you have really for the different scalar thing, complex scalar, SU2 doublet, U1 and SU2 gauge field, these shorthand notations where you have the energy for scalar, the kinetic, and then here the number of the field. So you start with 0, and then you have the amount of fields present. The same for gradient, and then accordingly to the complex and the SU2 doublets. For the gauge fields, we have here, they're indicated with A and B fields, and then as well kinetic and gradient energy. Okay, now if we consider as an example a simulation with 4 grid points, just very small, just to illustrate, and import again, let's say the kinetic energy snapshot into Mathematica, for example, we really have this list. So you have your kinetic energy snapshot of your first field at the 0th time here, and then you have here your different data sets, right? So this is the whole snapshot. Since we have only 4 grid points, it's fairly small, but it gets bigger. So for larger n grid, and you can simply imagine, right? So all these different sub levels of your list here really make up your whole lattice. Yeah, and this is what we want to plot eventually. Okay, before we go into more concrete examples how we can plot this, maybe a short word of caution. So these these files can get very big. For example, when you plot a simulation of one field with 128 grid points, required me, in my case, when I did a simulation, 70 megabytes, right? So if you go to 256 points, you need 8 times more space. And of course, if you do output more different components like the kinetic gradient whatsoever and have more fields, you need more and more space. So in case you simulate on a cluster where maybe storage is limited, or I don't know, someone pays for storage, you may think twice how many slices you want, how many snapshots you want to output, right? Could be very costly. So you see here this scales very, very, very crazy. Okay, so also for that case, for example, if you want to if you like to output the total energy of a single scalar field, you can also go to this snapshot measurement, energy snapshot measurer, and adapt it, right? So right now only the different components are outputted, but like, for example, the kinetic gradient and potential energy. But if you're just interested in the total energy of this, let's say, single real scalar field, then you may just directly output the total energy, right? And add the different kinetic gradient and potential energy directly in the CosmoLattice file, such that only one file is output and not three files, right? So there you can save a bit of storage. Okay. Now, having said that and giving this short introduction to how these files are structured and so forth, we go to small examples. The idea behind this is that we don't have assigned a particular practice session to plotting these snapshots. So I made this example as clear as possible, that you can basically do them by yourselves. If there are questions at some point, you of course you can ask me or write me even an email if questions pop up in the next couple of days or so. Before we go to concrete examples, we have to do a bit of preparation. So maybe if you haven't done it, we need to make your computer ready for this HDF5 library. So what you need to do is you need to go to this dependencies folder and install your HDF5 library. Either this first part here, if in case you're in the serial version, or you have to add this flag if you have the parallel version, right? Then what you need to do more is you need to put in your CMake list file here this is originally set to off, and you need to send it set to off, and you need to put on here that that your HDF5 library is enabled in principle. And it could happen, depending on computer, that you need to include a path here as well in this line. If you want to have more information on that, you can also just go to the appendix of the CosmoLattice manual, I think A3, where you find more information about that. But in principle, it should work if you do that. What's written in here. Okay, now coming to the first example. So what you want to do with that is that you are in principle able to make this video. Can you see it? I hope so. So there's a question.
Yes, we see. I can.
Okay, perfect. Yeah. So I can run once more. So this is nothing complicated. Exactly. So this is a movie of or series of snapshots of this model here, right? So you have seen it in the beginning, where the inferton rolls down the potential and enters by its oscillations into this tachyonic region again, right? So here once more a bit more specific, you see here the homogeneous, the absolute value of the field oscillating, and each time you see here the inflection point, which is here given by the dashed line. Each time it goes above the inflection point, you see how here the root mean square grows, right? So each time it's up here, it gets a kick and starts to grow until this nonlinear regime kicks in. Now we are only going to simulate this very first short time and on a very small lattice that you can do it on your computer. And then in the beginning, I've discussed this example also for oscillons which kick in later, but we only simulate this very first couple of time steps that you can do it with limited resources. Okay, so on the CosmoLattice school webpage, you find a couple of files. There are, I think, in total 6, but for this example, you need 3. And there are the model file, which is given here by tanesh2 hdf5.h, and then the input file, which is marked with the _1, right? And for evaluating your data, I prepared you this example one snapshot printer Mathematica notebook, which you can use as well. So if you, I think you know, yeah?
Sorry, I think there is a question. Isaac,
Oh.
you have your hand up.
Yes, so I just wanted to ask, so if I run a 512 cube simulation already, these files start to take up so much space. So I was wondering if there is an option or if it could be implemented. I mean, not you, but anyone at some point. So imagine that you real time, you co-generate the animation as you are running the simulation so that in principle, you can overwrite the files and just store one of them at a time. So this would then
wait again. Oh, sorry. So you're running a simulation on how many points?
Well, presume I run 512 cubes.
Oh, yeah. Okay. Yeah.
So really, this takes up an enormous amount of space.
Yeah, that's yeah.
So I don't want to do this in post. What I want to do is I want to generate a slice, or rather a full 3D dump, and kind of keep updating the animation as I run the simulation. Thus, this would allow me to essentially overwrite the dumps.
I understand your point. The problem is it would be very useless because you really need to play. Plotting is not immediate, you know, that you see things clearly. You need to tweak the color grading, where you sharp the features, etc. So you need to play to do post-processing, you know.
I understand.
Yeah, if you do it like that, you're gonna see nothing. Believe me, you know, really.
Yeah, or you have to know beforehand exactly.
Yeah, but to know it beforehand, you have to do the exercise you don't want to do.
Exactly. Yeah, I see. Okay, so I understand. Okay,
no, I understand your concern, but I'm afraid, yeah, I mean, it just wouldn't work like that because my experience, well, Ken can confirm because you've been doing this.
Yeah.
You need to play around with the data, no, until you see something beautiful, right?
Yeah.
Yes.
I mean, yeah. Sorry. Good that you mentioned that. I mean, maybe I haven't stressed that enough. So you should really make careful decisions on how many snapshots you output, what you want to investigate, and I mean, making a video is here mainly a fun thing, right? But sometimes you want to have just a single snapshot of, let's say, to see if there's structures like oscillons emerging, but then you maybe just output 1 or 2 slices at a particular point, right, to see what kind of structure emerges. So it's not behind making videos, not the idea to output now always 100 or 512 points and make tons of videos, right? That's not feasible somehow.
But technically, it's true that Isaac's point could be implemented. You know, I don't think it would be a big change in the code, but then it would be to the user, you know, to get that distribution, play around good enough that you see a good picture and be ready to erase it for the next iteration, you know, and you have to do that live and in real time. So it complicates the procedure, but in principle could be doable. It could be doable.
Yeah, sure.
Yeah. Yes, to give you an idea, for larger scale structure simulations, which are nothing to do with field theory, but anyway are very large simulations in terms of memory, they do that kind of technique you are asking about, because it weighs so much every single snapshot that they only do one snapshot at a time, you know, and that already occupies I don't know how many gigas or terabytes. Okay.
Okay, great. Yeah. So to continue here with this example, so we have these files here. You put your model file into your models folder, your input file in your parameters folder, as you did before. And then you can compile first your model file, where now, different to previous case, you have to put this HDF5 flag to on here, and then just simply compile your CosmoLattice file. And then running the code is just as usual. You have your model file here and your parameter file here, and you can just let it run. Then again, we have discussed this yesterday, or this questions appeared yesterday. So there will, for this particular example, there will appear a warning in the beginning of the simulations. This is because we are simulating now this tachyonic regime, where in principle the initial spectrum is not quite right. But I think for the purpose of this exercise, we ignore it and just continue simulating this case, and you will see in the end this video. However, if you want to investigate this scenario more thoroughly, you may need to think a bit more carefully about the initial spectrum. But I think for the purpose of this exercise, it's sufficient if we just ignore this warning. Then, so what have you simulated? So in input file, we have a simulation with 32 points, which should be feasible for you to do it on your own computer, presumably on your laptop or your notebook. And we've run it until a Tmax of 80 time steps, right? We have outputted here the kinetic, gradient and potential energy defined here, and we outputted at each time step, since we have put this output rare frequency to 1. So this is this T output rare frequency here really indicates how often you output a slice. So it's really here at each time step that we have one snapshot each. Okay, these snapshots are saved in these following 3 files, as you may have already guessed. And once the simulation is finished, you can plot these different energy components with this mathematical notebook that I've provided to you. I will, after I finished here with this PowerPoint, we go quickly into this notebooks, and I will show you how they're structured. So you have really here snapshots of these 3 different kinds of energy components. Here they're really it's really plotted the over energy densities in principle. So you have to gradient divided by the total energy, for example, and likewise for the others. We can also make these movies, as I told you, with this Mathematica notebook. So we do that in a very simple way, as classical movies have been done, I think. So we just make plots of each snapshot, save them in a film reel, as you see here. So you see here at the very beginning and until the very end, which is just in this notebook, just a very simple list, right? Or list contour plot, yeah. Where we have added the 3 different. So we plotted total energy density. So where we have added the different components, and you have here the different contours you want to plot, and the different styles, right? And then if you once have this list, you can just very, very simply export it as a movie, as you see down here. So this is all implemented in this Mathematica notebook. Okay. Now, the second example I want to go through with you are these oscillons. I've shown you at the beginning. So these are really, as I said, these metastable configurations, which are very long-lived and pulsate and yeah, are just there, sometimes moving a bit. To make these the plots for these oscillons, I thought you could try to adapt your energy snapshot measure, which you, as I said, found here, that you just output directly the total energy density of your scalar singlet. So you might need to get familiar with this file. And as you've seen before, the relevant lines of codes are already in this presentation. So I think it should be straightforward to do so. So we are just interested in the total energy density, and you can save a bit of space if you adapt your file here. So this second example has this tonnage HDF5 file 2 here with this _2 thing. And this is a bit a bigger simulation. So I'm not sure if it's feasible to do it on your MacBook or on your notebook. You might go to other resources. However, I put it here, and maybe you can adapt it a bit to still simulate. So we have 128 points, 0.01 a time step of 0.01, and now we are simulating here until 1,000 times. That's quite long, so only at a very late time these oscillons emerge, and we only output every 100th time step slice, and then here this would be the snapshot for the total energy density, right? In case you don't want to adapt your snapshot measure, you can just output again the single components and leave and change here the input file as follows. Now, if you have not compiled your model yet, you can again compile it as before and then run your simulations. Now, we haven't talked parallel computing yet, or how to use more than one core. This would be the way to do it. If you only have if you have only limited resources around, you may just calculate it on one core, and then you might want to adapt your input file. So if you have really not a cluster or whatever to your hand for simulation, you might want to change your grid size to 46 points and increase the time step a bit. Also, to capture this also more or less well, you might need to increase a bit your infrared momentum. Still, also here, if you have just on your computer, this simulation may take a while. So it could take actually a couple of hours to do so. If you have managed to do this simulation, you can use this example, this awesome plotter, the second Mathematica file, which outputs you this oscillon, these snapshots of this 3D snapshots of this overlay density. So you see here the contours, this light one and this dark one as the 10th and 4th and 40th contour of your energy density, over energy density. And then you have also 2D slices, right? Sometimes these contours are maybe not, they look beautiful, but are maybe not as useful as for example, to see here really how the energy density evolves if you really slice this 3D plot apart, right? Here you see these oscillons, how they're here, how large the energy densities are. Okay, with that, I have finished this presentation. And then I thought we quickly go to these Mathematica files that you get familiar with it. And then you should be able to do this simulation in principle on your own. If there are questions, I guess we may have time later or tomorrow to answer them. Or if you have already questions to the presentation here, we can answer them now. Okay, so Just
one suggestion. I think since Adrian is not going to join after the 5 minutes break, there's not going to be 5 minutes break. So essentially, go on with showing what you want to show. We address questions, and then we call it the morning. Once you finish. Okay.
Yeah, exactly. Yeah. No, I was more thinking if some people have questions after they have tried to make these simulations, right?
Of course, that we can address in the morning session. Of course.
Exactly. That's actually the idea.
Thank you.
Okay, perfect. So this is, as you see here, sorry, it's in a way this example snapshot measure, this for the example one, this Mathematica notebook. I think everything is adapted in such a way that it should directly work with the simulation. If you change anything in the simulation, you might need to change the grid. Here, the number of grid points, which is now adapted to 32. And also, if you output less or more slices, you need to maybe change this number here. Okay, so the first snapshot is maybe we look here at the kinetic energy density snapshot. So as you've seen before in the presentation, you can just import this file and put summary here in the back, and it gives you all the basic data about this HDF5 file. Right. You can also have this structure graph, which should give you something similar as you've seen in the presentation before. However, there's so many snapshots that you can't see much. In the next file, you see it a bit better. Now, up here, we've put together this function which plots you the kinetic energy snapshot, and it works as follows. So here you can choose your type of scalar field. So you can not only should be able to put in here different types of fields, not only the scalar but also the complex or the SU2 doublet. Then you have to look here how many fields you want your simulations have. So the current simulation just have one field. Then you can choose here the snapshot you want to print. Here it's the 70th snapshot we're printing now. Then you can put here the contours you want to have. This is a 3rd and 8th contour, and you can here choose the style of your contour. So you put all these parameters in here. Sorry, you put all these parameters in here, and it should output you really this this snapshot of this 70th this 70th snapshot of the kinetic energy density, right? What you also have in here is just a 2D slice of your of this particular snapshot. So we take here again these other parameters, these old parameters from above, but specify again the your favorite slice to this slice through this 3D cube, right? So here it's now this 20th slice. It's probably somewhere on the bottom where you just print your kinetic energy out. So it looks a bit spiky. That's really due to the resolution that we only have 32 points. Yeah. So this is for the kinetic energy. Then you have the same for the gradient here in blue, and for the potential energy, which may look different. You can also put these different files together in one, if you like, to show maybe how these different components evolve together. Then I think you can do that just by show different plots. Okay. The second thing we discussed, or what was the main aim of this example, was to make this movie. Again, it is in this sub for the movie, where we have now where we import these different components here, as you see, and then here in the bottom part we can you can become your own filmmaker, where you have to pick choose a couple of parameters that are which contours you want to plot, and then also the style, which we have put here in green. Then you have your film reel, as I've showed you before, and then you can just output the movie, as you see here. Now, before I showed you a very long movie, the particular movie you will be outputting here may look as the following. Oh, they're not working. Unfortunate. So this is the movie you will output with this particular simulation. So in the beginning, you will see not much, right? That's the reason is really because we picked some very large contours, and until the resonance builds up this fluctuation, it takes a bit of time. So don't be worried if this takes a moment. Then also the resolution is not very high, so maybe you want to adapt this. However, these files can get fairly large, so that's what you need to decide on your own, how to deal with that. Again, you see here now these fluctuations emerge. Okay, then what you could also do is you could just output a movie of your 2D slice in this lower part here, if you like to just see how these types down here, how these types of plots here evolve, for example. Okay, this is the file for the first example. Then the second example is here, this oscillon plotter I've given you. Again, it starts similarly. We have to specify our grid points, then your output graph frequency. So if you do a smaller simulation, you may have to go here down to 46 or whatever, or maybe even 32. I keep it here at 128 quickly. Then what I've included also for you is here just the evolution of some average quantities. So you see here how the absolute value of your field evolves, and then how this root mean square evolves. I think the first plot in the that was the first plot in example 1 actually. And then also how the energy densities evolve. Also, yeah, that plot was in the second example. Okay. Then here you have again your summary of your snapshot. You'll see here this 128 file already contains 34 megabyte. It's already quite a bit larger, and it has only 8 slices in it. So if you want to output more slices, these files get very big. Then again, you have here the structure graph now, which you can see here now a bit better. So with your group, and then down here with your data sets, it even tells you in Mathematica with this small inset here. Okay, then you have this oscillon plotter, also a function which just outputs you here this 3D plot. Where you again have to pick your particular snapshot you want to investigate, and then the contours you would like to have, as well as the contour style. Unfortunately, I've seen that there was a small mistake. At first, I haven't been able to spell here length correctly. It should be that the H is on the wrong side. So, so this file is right now on the web page. We will after the lecture we will upload a corrected version of it, right? And then the other mistake, somehow it was 0 instead of T. So if you want to apply it right now, you should make these changes in here. Otherwise, you can just wait until we upload the new file. It should be there latest by tomorrow. And then I'm sorry for that. And yeah, so these are the 3D snapshots, and then you can also have like as I showed you before, just these slices through these 3D snapshots here. Wait. Oh, okay, good. Like just this slices where you see here the oscillons, how the amplitude of these oscillons are, right? Here, unfortunately, the same error happened. I just copied it and didn't correct it. So you may need to correct it here as well. Perfect. So far, so it. Are there questions? This would be up to this point all of all from me. Yeah, does anyone have any question?
Yeah, thanks for the practice demonstration, Ken. Yeah, I see there is Antonino. Okay, please, you can go ahead.
Yes, thank you very much for the presentation. My question actually is very basic, related to the simulation we did this morning in the practice session with the gravitational waves in the hyperbolic tangent model. Because I'm using the notebook in Mathematica and I'm trying to reproduce the same kind of text to plot the gravitational wave spectrum, but I didn't manage to do that, and I don't know, because I'm not very much experienced with Mathematica. So I want to ask you if there is some specific moment in which it is proper to maybe show my screen, and that you can suggest me something.
Yeah, sure. I mean, we can do it at some point later if you like. So we, as I heard of you that you would like to do that in private somehow.
Okay.
Or was that a request from you that we can do it, that you can show it later at some point just to one of us?
Mm-hmm.
Or would you want to show it here in public?
For me, it's the same. I don't know if it's useful for the others. Maybe there are some questions which are more technical. Mine is very basic, so.
Okay, but it's not directly related to printing now these snapshots or these field values, right?
No, exactly, no.
Okay,
basic.
Then maybe I would suggest that maybe if there's some more questions, I see one here, particular to this topic, then maybe we just answer them first, and then we can come back to it. Is that fine for you?
Sounds good.
Okay. Okay, perfect.
Thank you.
Okay, then Alessio. Hi, Alessio.
Alejandro.
Sorry. It's there. I was reading now the chat.
Hi, yes, I also had a question.
Okay, sorry.
Alessio, okay, sorry.
It's not my turn.
No, yeah, continue, and I will come back to Alessio afterwards. Yeah, Alejandro?
Hi, so should I ask my question?
Yeah, sure.
Yeah, hi, thanks for the lecture. So maybe you mentioned this, sorry, that is the case, but can we do a snapshots of other background quantities aside for energies, like for instance, the expansion factor or things like that to visualize co-moving hypersurfaces, or is just prepared for energies?
It's just prepared for energies and probably for the field values, right?
Okay.
How do you mean by the expansion?
Expansion is continuous, Alejandro. There is no point in plotting nothing in 3D.
But so the TXT file for the expansion factor is average, right?
Sorry?
Yeah.
So if the let me open there is a TXT file which is average scale factor, right?
Mm-hmm.
In the output.
But the scale factor is not average. That's what I'm saying. You compute the scale factor from the average of the field distribution.
Okay. It's not computed for each point like the local scale factor and the average.
Well, I mean, maybe those two operations are equivalent, but in any case, the point is the meaning of the scale factor is a global quantity describing the space in a larger scale, where you are averaging out the local inhomogeneities of the field distribution. It's pretty much the same view as in late universe expansion, where you have galaxies and you still talk about the homogeneous isotropic distribution of this matter in the universe, which doesn't mean that locally they are homogeneous and isotropic. No, locally the galaxy is very inhomogeneous. This is the same, but with fields. So at the global scale, which translates into larger length scales than the typical wavelength of your inhomogeneities, this is a statistical homogeneous isotropic universe, and there is one scale factor for all of them. And then locally you are developing inhomogeneities. Okay.
Okay. But the field value is tracked locally.
The field values, the matter fields develop local inhomogeneities, fully local with gradients and whatever you want. but they live in a global space.
Yeah. No, I got it. I got it now. Yeah. Because I was thinking about something like so what people do like in delta informalism and so on, in which you have like this local scale factor, but I guess you're not tracking this here, right?
No, that would be too difficult because delta informalism, you need to go to compare like different. How you could do delta informalism here is running different realizations of the same volume, you know, because at the end delta informalism is nothing but capturing the statistics of your fluctuations, you know. So if you run different, same simulation but with different initial seed, you could try to do delta informalism comparing the output of the different runs. Yeah.
Okay.
It's been done, by the way, in lattice simulation, not with CosmoLattice, but far in the past. In 2009, 7 to 9, Artur Rajanti from Imperial College used that technique. Yeah.
Okay, I'll check that. Thanks very much.
Alessio, now maybe.
Okay, exactly. Yeah. Quickly turn to Alessio. I think it was in the chat. For a single point of the grid.
Do you want to read out the question?
Sorry, yeah. The question in the chat is, hi, a very basic question. Is it possible to print the time evolution of a field value for a single point of the grid? I guess in principle, yes, right? Because you output the whole lattice, you just have to pick one.
Yeah.
Could be a bit annoying.
Yeah, sure. I know in principle, yes. I was asking if there is a simple practice.
I mean, I think if you can, I think I would assume it shouldn't be too difficult, right? In mathematics, you could just enter a sub layer of your list and then just pick out one value. So yeah, I think it shouldn't be, yeah.
I don't know, but I want to do it at all times. I don't want a snapshot of the field everywhere.
You could modify the code, you know, to have.
Yeah, I know, but I was asking if there is already some.
No, so you should be. It shouldn't be very difficult to do. That's something it should be relatively straightforward to do once you get used to a couple different aspects of the code, like how files are written and how you can access values in the file. But that's something you could do, and it won't take a lot once you know the code. The only subtlety is the way in which you choose the point. But that's something, yeah, that depends on your choice.
No, because maybe a related question is if I can print averages on a subset of the box, just a smaller region.
Yeah, I mean, you can do this. You need to implement this, but that's something you can implement. For instance, you could try to implement like some quantity, which is an average of a quantity multiplied by a heaviside function, which is one only inside some region. And so you restrict your average to that particular region. That's something you can do.
You need to include your own observable to do that. Yeah, because of course it's very peculiar observable. So
you will need to be careful with the normalization, because if you try to use the default average, it will be assuming you are using the whole lattice. So probably you need to be careful with that. But in principle, it's just defining your own observable and then saying to one of the files that print an extra column with that observable.
Yeah, on the other hand, the theta function idea you just said would be still wasting a bit resources, no? Because then it would be putting 0 while sampling a bunch of the lattice. So maybe what you want to do is implement your own mean value, solver, if you want, and then determine which subvolume you want to survey, you know.
Yeah, but that's, so the first thing I was suggesting, you can do that in probably an afternoon or a part of an afternoon, doing the implementing your own average here to work in a sublattice. It's probably, it may take you a bit more.
Yes, but okay, Alessio is getting well inside the code. I know that for certain.
Okay. No, but a related thing which could be useful, I think, could be to have also the snapshots say a coarse-grained snapshot?
Yeah, but
Because now
you do a
these snapshots
posteriori.
for large simulations are extremely heavy. So
Yeah,
sometimes I would like to visualize only.
yeah.
That's also something you can, I mean, you have to modify. So one thing we did is doing a snapshots of a subvolume. And that's something we did, for example, for this string project we've been working on. And then doing the coarse graining version of the snapshot is also something that you need to go into the code and modify a couple of things, but it's something you can do.
No, these are all doable things. I mean, just
Yeah.
ask if any of them is already implemented or
No,
easy to do.
So that one's something we thought about.
Yeah, but at degree of functionality, Alessia, I'm not sure we can provide that, you know, because, you know, at the end, for each specific run, people, you know, may think of different kind of circumstances of this kind. And I think that's something you have to do in processing or just modify yourself the code to do it, you know. Yeah, because I don't think we are going to ever release something like that, you know. Well, the coarse graining could.
The coarse graining maybe.
Coarse graining, the sub-volume averaging or one single point averaging is too specific, you know. Yeah, and
yeah, but the coarse graining is something I think it's
on the other hand, again, I think if one goes inside the code, well, it should be you know, relatively straightforward to do those modifications, you know, by following what the code is doing, of course. Yeah.
Sure. Thanks. No, I think the coarse graining will be useful because these files are huge.
No,
yeah,
you are right. You are right, but the coarse graining blindly by doing like, okay, we do now every 2 lattice sites, 3 lattice sites. Yeah, it could be. It could be. We could think of that. We could think of that. But yeah, we'll see, you know, at some point.
Thanks. Okay, Isaac, I see your hand.
So this is not so much a question, but potentially a suggestion. So I mean, I was just thinking, instead of actually saving the whole 3D grid each time, couldn't you already at runtime save just, let's say, equi-energy surfaces, which would reduce this? You would basically not save 3D data, but 2D data, because the number of points would scale with the areas of these surfaces. So you wouldn't save the actual grid points and the corresponding values, but you would rather save the value and the grid point, the XYZ coordinates to a file, and really just save those locations so that you just save the surfaces.
You could think of designing you know, an observable like that, so an algorithm that saves that, but then you have to reconstruct the 3D distribution with zeros afterwards for the typical plotting programs, you know, which take as an input a 3D distribution.
Yeah.
So yeah, it
will
like
become
a nice
work.
idea to save to save memory. I understand your point, but yeah, you will have to do that yourself. And good luck with plotting that then, because probably you really need to recreate now with zeros the file, and then you go into the same problem very likely, you know.
Yeah. Okay. Yeah, I see.
But theoretically, yes, it should be possible, you know, feasible, you know. Okay, more questions.
Okay, so
to Ken or
exactly. So I see no more questions relating to this. So we could come back to you, Antonio, if you like, or we can also discuss it later if you wish.
Yes, thank you. So I don't know, maybe I can share my screen. Maybe
Yeah,
it's
I can stop here. I mean, I'm not sure. Maybe you can also stop recording if you prefer that.
Yes, as you like, yes.
Well, that's not on me actually. It's on Danny.
Yes, probably we can stop recording. That's
Danny?
basic, yes.
sure. Let me stop.